Okay, so we're going to, so the name of the enzyme we're going to talk about is, it's called, well, it's not heparinase, but it's an heparinase-like enzyme because it is similar, but it is not equal to heparinase. So first we're going to talk about snake bites and what they do to your body. So,
I want to talk about snake bites. What are the symptoms of a snake bite? The symptoms that result from a bite of a venomous snake will depend on the type of snake that is involved. Some common reactions include the following: two puncture wounds at the site of the bite. However, the pain it's not always a symptom. For example, the coral snake can be nearly painless, but at first, but still deadly. And the other symptoms are redness, swelling, and damaged tissue, abnormal blood clotting and bleeding, low blood pressure and shock, nausea,
vomiting.
Difficulty breathing, or in serious case not be able to breathe at all, blurred vision, increased production of saliva, heavy sweating, not feeling in the face or limbs.
Okay. Here we have here we have a video of what snake venom can do to your blood. So we're going to. Now we saw what the venom can do to the blood, forming blood. So my friend Liz is going to talk about it. Oh, she's in the herpetology lab, so she has managed to snakes. She has expertise in it.
Haciendo hincapié en lo que había dicho Sandra antes, del veneno y de las dificultades que causa, aquí hay un problema en México. No tenemos curas. O sea, tenemos el veneno, pero México no da lo que es dinero para ayudar al estudio y que se puedan hacer antídotos. Entonces, generalmente aquí tienes que, pues suerte si te picó una y que traigan el antídoto, porque el antídoto no es de aquí, lo envían a Alemania. Razón por la cual en mi laboratorio no tenemos antiveneno, y si nos muerde algo, ahí quedamos. Y eso lo cubre, porque todo está bien. Anyways, the crocodile family and some species of botrops, which are from the Viperidae family, have these heparinase-like enzymes which cause the clots inside the body of its victim, normally rats, or wherever they find actually. And it's a heat-stable enzyme, which makes it hard to denaturalize. Pre-resistant. I don't know how to work on people. When the heparin from botrops atrox, this one, it's put in for 60 minutes in 37 degrees, it loses most of its anticoagulant activity. Actually, there's studies of these snake venoms, which they inject a lamb with it. Sometimes the lamb dies, but the point is to take blood each hour and measure it in tubes, and they keep it tabs, so you see how much coagulation it has. When the venom has already spun around and survived, in this case, it does, and how it slowly becomes a blood liquid what's in it. Proteins. I'm pretty sure Torres already told you this. Well, sometimes formed by hydrolysis. That's all you need to know. It's super easy actually. And they contain tens of thousands of proteins in cells, which make different biological activities. They can be pretty long polypeptide chains, or the oligo. The protein structure. 4 levels of proteins. You already saw it.
Yeah, they already know about You can ask them if you want.
Oh, sure.
Era lo que hacía con una hoja, ¿verdad? De que
Bored.
You have protein of one.
The name of this, like, project is pretty simple.
Farther.
Hemoglobin.
Yeah, you're denying hemoglobin.
Yeah.
It's usually the most common thing like
Now I'm going to have to talk about enzymes because our protein is an enzyme. So I'm pretty sure you already know that too. But well, enzymes bind and chemically transform like molecules, so they catalyze reaction that makes them go faster. The molecules that act upon enzymes are called substrates, and the ligand binding is called the catalytic or active site. The binding of the substrate to the enzyme causes changes in the distribution of the electrons in the chemical bonds of the substrate and, well, causes the reactions to lead to the formation of products. Well, here we have like a simple enzyme. It has the active site, that is where the whole catalysis takes place, and we have the substrate. This figure of an enzyme catalyzed reaction that is displayed in the contents of the enzyme. And here you can see we have the enzyme and the substrate, and then you have this enzyme substrate complex, the enzyme and the product complex, the enzyme product and release. Yeah, inside. And you probably heard about the locking key theory.
Yes.
It was first postulated in 1895 by Emil Fischer. And it's really simple. Just like just one key can open one lock, just one enzyme can perform a certain job in a molecule. Well, the characteristic of enzymes is that they are very specific, and well, just the correct shape of the molecules can fit into the enzyme, just like the key unlock.
What was the name of the other model guys? Besides the lock and key?
And then where the enzyme like binds, no? Like, or flexes.
Like the best feed.
Best feed
It induces a conformational change in the active site.
Best feed's not
After the reaction, it restores to its normal form.
Best feed.
Enzymes are catalyzers. We can see here in the graph the reaction with and without an enzyme. As we can see, is without the enzyme, it requires more energy, and with the enzyme, it requires less energy. Because of that, like simple things, just like degrade like nutrient molecules, just like for your brain to send the signal to the muscles to move, will take like longer than without an enzyme. So enzymes are really important for everything in life. So enzyme. And well, you already know about neutralization. Like molecules are quite stable in neutral pH and temperature, but as we all know, also like that's not something that is just natural. Like there might be like when you test things in the stomach, there's like different pH concentration and stuff like that. So things can change and the reaction can stop like that. And here we have also like every enzyme, like everything in life has like an exponential growth. Then it reaches the optimum pH or temperature when they work at the optimum, and then after that they fall. Usually the optimum temperature for like everything is, including enzymes, is like 36 degrees and stuff, and the pH was 7. And after that it is fall. Yeah.
Okay, so I'm going to talk about the enzyme we saw that was in the snake venom. And what this enzyme, to understand what this enzyme does, we first have to see what the beta-heparin does. So beta-heparin is it's an enzyme also in our bodies that's called dermatan sulfate, and it's naturally produced in our bodies. It can be found mainly in skin, blood vessels, heart valves, tendons, lungs, and intestinal mucosa. Yeah, and well, it's thought to be involved in wound repair and regulation of blood coagulation. That's what related to what we saw earlier in that video. So next. So it is a natural anticoagulant, an antithrombotic. Antithrombotic, the origin of the word is from thrombin. Thrombin is an enzyme that causes the clots in our system. So what beta heparin does is stop like thrombin number 3 from producing clots in our body. So yeah, the well-documented interaction of dermatan is binding of dermatan sulfate to heparin cofactor 2, which is, cofactor is something that helps an enzyme do its job, which acts by inhibiting the procoagulant activity of thrombin. So if we didn't have heparin, a lot of clots would form in our body. So what does heparinase do? Well, heparinase destroys heparin. So how does it do it? Heparinase is a lytic enzyme, which means it causes lysis. Lysis is the breaking down of the membrane of the cell. So since heparinase does lysis on heparin, it destroys it, and so it can cause clots to form in our body. Next. So how does it destroy heparin? Well, heparinase cleaves the glycosidic bonds. Okay, so heparinase cleaves the glycosidic bonds between the amino acid that forms the chain that makes the protein work. So when it destroys these glycosidic bonds, it forms the products, which are these separate, I don't know the scientific names, but it mostly separate these amino acids that turn the chain away. So next. So then we can see here is a long chain that forms the heparin, and here are the attachments in which heparinase 1, for example, heparinase 1, 2, and 3 attack, and heparinase 1 and 2 attack. So yeah, the names are N-acetyl D-glucosamine, D-glucuronic acid, D-glucosamine, and all the other amino acids which it cuts. And well, heparinase cleaves the binding site of the antithrombin 3. Okay, so the name is pretty obvious. Since it is antithrombin 3, it means that it inhibits the clot forming of thrombin. So I think it's a little convoluted, but if heparinase cleaves the binding site of thrombin in heparin, of antithrombin in heparin, then antithrombin can act with thrombin to stop the clot from forming. So that's the whole process, and that's why when a snake bites us, it can form clots in our blood system. Okay, heparinase cleaves heparin.
And heparin is a natural
Anticoagulant.
anticoagulant.
And that's why it forms clots. Yeah. That's basically it.
Okay, y eso tiene el veneno de la...
No.
O sea,
No question. Because it could be in the camera. I know. I mean, and it's not in the wiki. Trust me. It's not in the wiki.
It's in the wiki.
Why not? It's an example of how the immune system could be attacked by a snake venom. Oh.
Yes, en what does the immune system